Hi there. Today we're going to talk about what we've already kind of mentioned, namely BodePlots, and this is a convenient way to represent the frequency response of an AC circuit. My name is Vivek Subramanian.
And I'm Michelle Maharbis. All right, let's get started. So first, let's do a quick review. This is a complete review of the last module. So when we're dealing with the types of circuits and the concept of frequency response in this module, we're specifically talking about looking at the properties of a transfer function, wherein we put in an input and we solve for the output, and both of these things are essentially a function of the frequency omega.
And remember, this is for sinusoids.
That's right. So the transfer function h comes from some output. In this case, we're choosing the voltage on some element or combination of elements, divided by some input, again, both of which have an omega term in them. And because we're writing it this way, this h of omega will be a complex number. We can break up that complex number, or rather we can express that complex number in this polar form where there's a magnitude and e to the j phase, so there's a phase. Both of these will be functions of omega. We discussed this last time. So this m always refers to the magnitude of the h, and this phase, which comes from arctan of the imaginary or of the real part of h, refers to the phase. Okay, so what we're going to do is the following. We're first going to introduce something called the decibel scale, and we'll explain why. And then we're just going to go through a bunch of plots. And we're going to show you how to plot this, and at the end show you why we do a specific kind of plot called a BodePlot. And that'll be the end of the module. So Vivek, want to take it from here?
Sure, since you didn't actually teach them anything new, I can start something new.
Grumble, grumble, grumble.
Grumble, grumble. All right, so let's go. We're going to talk about the decibel scale, and this is an important scale because it turns out to be a very convenient way to represent functions that change by significant amounts because, as you're going to see, it's a logarithmic scale. So let's go ahead and set that up. Now, I will start by telling you that the decibel scale, we always talk about things in terms of power gain. Okay, that's how we define the decibel scale. So let's say we define a power gain as the ratio of some output power to some reference power, which could be an input power P0. Okay, so then what we have is G, the power gain is P divided by P0. That would be some number. If we were to take the log of that number, we would be defining a term called the gain in units of decibels. Okay? So the gain, if it's a power gain, what are the units of G going to be, Michelle?
The units of G are going to be unitless.
Exactly, because both are power, right? So this is power and this is power, so it's going to be unitless, which means we can take a log of it, and we will now get something that is unitless, but because we are now defining it as a log scale, we will call it something to do with a bell.
So, wait, to be clear though, it's 10 times the log, right?
I haven't said that yet. I said a bell. I didn't say a decibel yet.
All right.
All right. Now, what we do is we actually, rather than using a bell scale, we use a decibel scale because that turns out to give us a sort of a more representative and important range of information. And rather than plotting the log of G, we plot 10 times the log of G. And the D comes from deci, right. So you get the representation of the factor of 10. Okay? So that's why we... Now, you may sit there and say, well, why did we pick this? It turns out for real systems this gives a useful range of gains, and over a typical frequency range it'll give a good spread in the data. Okay, so that's why this is a useful scale to work with.
So basically what you're saying is that in these circuits, in many circuits, there's a wide range of powers and power gains we're dealing with, and we'd like something that spreads that out. Okay.
Exactly. That's why we do this, and decibels happens to be a good range.
Okay.
Okay? All right. And so then we get 10 log G, which if we were doing it in terms of the original power will be 10 log P over P0, and we call that in units of decibels. Okay. Now, this is in terms of power. Of course, generally when we do circuit analysis, we're doing calculations in terms of voltages or currents. Remember that you can always convert. And specifically, you recognize that power is half V squared over R, for example, and if we were to convert, we just take the square and we move it outside and we'll get it in terms of 20 log. So what does this mean? This means then when you're doing decibel scale plots for voltage, instead of having 10 log of the gain, if you're doing it for voltage gain, it's going to be 20 log of the gain.
So I notice a lot of people get this confused, even professional engineers. So often it's not really made clear what you're looking at when you're looking at a decibel scale. And you should make sure you understand whatever information was given to you, whether it was a voltage or current gain versus a power gain, because there's a factor of 2 there.
Right. So remember, current gain will also have a square, so you'll get a 20 log. It'll just be I square R, right? But it's in power gain, it'll only be a factor of 10 that goes in there. Okay. Now, why are we doing this? What's the whole point of doing this decibel scale stuff? Well, I'm going to give you some information to sort of lead you into it, and then when Michelle starts walking through doing plots, you'll see how this makes sense. So think about any circuit analysis. If we're doing some sort of gain functions, let's consider we have 3 amplifiers end to end, okay, connected in series.
Okay.
And each of those has a gain. Let's say gain is A1, A2, and A3.
Okay.
What do you think the gain of the overall system is, Michelle?
A1 times A2 times A3.
Right. And so you'll see that's pretty common. When we have multiple blocks connected end to end, the gains are multiplied by each other.
Okay.
Now, in a log scale, remember that a multiple of 2 functions in a log scale will be written as an addition of the logs of those functions. Similarly, the division of 2 functions will be the subtraction, the difference. Now, why is that important? Graphically, doing additions and subtractions are really easy.
Oh, I see. So if you've got a filter that at some particular point reduces something by 3 dB, and you've got another filter that reduces it by 3 dB, the total reduction is 6 dB.
Right.
And I didn't have to go about multiplying a half by half.
Exactly. So remember, the key point is, as you'll see in a second, when we're dealing with dB, things are done by additions and subtractions rather than by multiplications. And that's just easier to deal with.
All right. Well,
Okay?
we'll see that in a second.
All right. Now, having said that, Michelle said 3 dB, and why did he pick 3 dB? That seems like an odd number
I was
to
just
pick.
guessing. It was a lucky guess.
Yeah, it was a lucky guess. All right. So here's the reason that this comes out, okay? So Michelle, when we talked about cutoff frequencies, what was the power point of the cutoff frequencies?
So it's the point at which the power dropped to half of its maximum value.
Exactly. Now, if you take that information and you calculate what that represents on a dB scale, it turns out the half power point is 3 dB lower than my peak. So if my peak was defined at the 0 dB, let's say it was a system which at its peak had a gain of 1. In other words, the full frequency the full magnitude got through, then the half power point will be 3 dB down. And correspondingly, if there was something that was not 3 dB higher, that means we would have increased power by a factor of 2. Okay, that's the first thing to note. The other thing to note is, of course, being a log scale, every time you increase the dB by 10, that corresponds to a multiple of 10 on the absolute power scale. So for example, going from 0 dB to 10 dB means you've gone from a power gain of 1 to a power gain of 10, and then going from 10 to 20 dB means you're going from 10 to 100.
So that means if I see something that's 90 dB higher, it's 10 to the 9th times
Yeah, it's
bigger.
exactly. It's a huge change. Now you see why this is useful, because with the dB scale, I can cover a huge variation in gain and still get plots that are easy to deal with.
And it's symmetric with respect to big and little numbers. So minus 10 to the minus 9, so 1 nano of something is basically minus 90.
Exactly. Now, of course, all of this is done for power. If we were doing it for voltage, there's a factor of 2 that goes into that, because, of course, instead of being 10 log something, it becomes 20 log something. So if we're doing it in terms of voltage, the dB scales are spread by a factor of 2. And the same would be true for current.
Fair enough. Let's do an example. Let's put all this to work. So what I'm going to do is take an RL circuit. Instead of doing an RC like the last module, we'll just do a little different. And I'm going to do something very similar. I'm going to define a transfer function, which is the output across this inductor versus the input.
Nice to see you doing some work, Michelle.
Well, I would argue this is marginally more work. I'm taking a lazy way out, doing something simple. Okay, so this is, again, an impedance or a voltage divider, right? So this V out is just going to be j omega L divided by the sum of these, R plus j omega L, times the source voltage. That'll be this voltage.
So that's just a voltage divider right
divider,
there.
Yeah. So now I've got this. Now if I divide V out by Vs, in other words, I bring the Vs over, I get the ratio, and that's my transfer function, right? That's the thing I'm looking
Yeah,
for.
and that's a voltage transfer function specifically.
That's right, so we'll see that in a minute. And so if I do that, then I get this part by itself, j omega L over R plus j omega L. Now what we're going to do, and this is a very little trick, but it is a trick, is we're going to divide out so that the expression is in this form. And you'll see this a lot in BodePlots. It's omega over some reference frequency, which happens to be the corner frequency. So omega over omega c.
Okay, so I see. So what you're doing is you're taking some presuppositions. I mean, you know something, right? Because you know what the corner frequency is and you're going to divide by it.
Yeah, effectively, the corner frequency of this system turns out to be R over L. You could have arrived at that by saying, that I know it's R over L, let's divide out and cast in this form. Or, you know, I guess more generally, you could just tell someone, take this expression and cast it in a form that is normalized out the frequencies.
And just as a reminder, could you explain, if I didn't know what the corner frequency was from that transfer function, how I would find the corner frequency?
Oh, if you didn't know what it was, so what you would take your transfer function,
Yep.
write out the magnitude, and then find the place at which the magnitude equals 1 over square root of 2 of its full.
Got it. And that's because there's a voltage transfer function, so the half power point is 0.707
Exactly.
times the peak magnitude.
Right. It's exactly what we did for the RC example in the last module. So now what we've got is we've got our transfer function written this way. I'm not suggesting all of you will instantly look at this and go, of course, I know how to do this. But take a moment. We'll give you lots of practice in going from this expression, which is pretty straightforward, to casting it this way. But it can be done. And what you're doing, again, is you're normalizing all the frequency components to something, right? So if this expression is 1, you're at the corner frequency, right? Omega is omega c, so this went to 1. It'll become important in a minute. Now, having put it in this form, I'm going to take the magnitude, which I know how to do, so I'm going to write that out here. And we're then going to cast it into the decibel scale.
Okay, and I'm going to guess, because this is a voltage gain, it's going to be the 20 log form.
There you go. So 20 log of m, this is m. Now look, this is where it gets neat. Because this is a fraction, once I take the log of it, the log of this fraction is just the 20 times log of the numerator minus, because it's a division, 20 times log of the denominator. See?
I see. Okay, and because it's a fraction, I don't actually have to do the division in the log scale. I just subtract them.
Yeah, you just have two terms, and now the other little wrinkle, which is pretty straightforward, is if there's a half, exponent on the log, you can just bring it down.
I see, and that's because this is the denominator is a square root. Right. Ah, I get it. So I get a half, and then in the log form, that's just the same as dividing by 2.
Right. I could have put a square root here, but instead I put a half just to show you that that's what happens with the log.
Easy.
So now, what does that mean? On a decibel scale, if I were to plot y-axis decibels and x-axis frequency, I'll see these two terms. I should see these two things. Essentially, if I can look at and plot what these two terms are and subtract them, I'll get the actual complete response. So what we're going to do is we're going to do that. Now, the only trick is I'm also going to plot omega on a log axis. Okay, so you can see this is a log. This is 0.1 omega c, and 10 times omega c. Why am I doing it as a function of omega c? Well, because I didn't give you any numbers. So I'm keeping all of this symbolic, and so I'm centering it on omega c. Notice also that the y-axis is decibel. It looks linear because we've got 1 decibel, 2 decibel, 3 decibel, but decibels are...
Right, that makes sense because the decibels themselves are log scales. Now, a thing that's worth noting here is the reason we're plotting versus omega c and we're doing things in sort of log form is look at each of these terms. And if you look at each of these terms, it's 20 times the log of something divided by omega c. Right? And if you're looking at a log form, well, you know that if you have two things dividing each other in that way, or one thing dividing another in that way, that's really a subtraction. So it'll make it into a linear element when we do it in a log form. Yeah. And so we'd expect it to be a slope with a straight line.
Yeah, and that's exactly what we'll do. So let's take a look. That's what will happen. So let's look at the first component. And so here I'm plotting the individual components in blue first. The first component is 20 times log of omega over omega c.
Let me interrupt you. So what you just said that you're going to separate them out. I get it. So because we're going to be doing a subtraction, you're going to plot first the term corresponding to 20 log omega c. Then you're going to plot the other one corresponding to 10 log, etc. And then you're going to combine them together.
Yeah, and then I'm going to subtract one from the other.
Got it.
So the first term on this type of plot is going to give us a straight line with a slope of 20 dB per decade in frequency.
And that makes sense to me, but let's think about what that means. first, what is a decade? A decade is 1 order of magnitude change.
10x.
10x. Now, 10x on a log plot means 1.
That's right.
And change the log value is a change of 1. And then I'm multiplying it by 20. I get it. That's why it's 1 per decade multiplied by 20, so it's 20 dB per decade.
Right. For every 10x we jump this way or that way, right? This is omega c, then 10 times omega c. We'll have gone up by 20. And you can see that here because it's what you were saying earlier. If I'm at omega c, it's omega c over omega c, log of that, log of 1. So I'm
and that's 0, right?
Yep. And then if I do 10 times omega c, I've hopped up to here, that omega c's drop out and I get log of 10 times 20.
Okay.
There I am, 20.
Got it. Log of 10 is 1 times 20.
And so on. And you can keep going. If I had 100, then this would go up to 40. And so you get a slope of 20 dB for every jump in 10.
Okay. And we call it slopes even though it's on a semi-log plot, just because it's a slope per decade, because the x-axis is in logs.
Yeah.
So don't let that surprise you, okay? If you see this sort of 20 dB per decade, that indicates a slope on a semi-log plot.
Yeah, and decade, as you said, it just means 10x on the x-axis. So let's look at the other term. The other term is 10 log of 1 plus this business here, right?
Yep.
And so what you'll find is that for basically for a very low, so for when this thing goes to 0, this is log of 1,
yep.
0, so you start up here.
And specifically this is you're subtracting it, right? So it's minus 10 log of 1 plus omega c squared, right?
Oh, you're right. That's exactly right. In fact, I hadn't noticed that when I started talking. That's right. It's a minus, so this thing's going to go down.
Right.
And so that's exactly what happens. So anyway, this starts out for omega being 0, this goes to 1, log of 1 is 0, so we start here. And then as omega increases, this number will go up. And eventually, for very large omega, this 1 doesn't really matter. So I get minus 10 log of omega squared over omega c squared, and so I get minus 20 dB per decade going down.
Well, let me go a little slow, just so I get that. Okay, so first let's take the case where omega is really, really small.
Okay.
Okay, now when omega is really, really small, the omega over omega c disappears relative to the 1. And so I'm taking minus 10 log of 1. Well, log of 1 is 0, so it's going to be start at 0. Okay, for really small omegas, it's going to be 0.
What to do very large?
All right, let's do really large omegas. So really large omegas, well, let's see, omega over omega c will tend towards some very large number. The log of a very large number will be a very large number, but I have a minus sign, so it's going to tend towards some sort of very large number with a negative.
Moreover, the 1 doesn't matter, right?
Right.
So remember when we had a square here before? So now you have minus 10 log omega over omega c squared, because we're ignoring the 1 for a very large number. So what would we do with the 10?
Okay, so if it's for a very large number, that square can move out, and we just multiply and it becomes 20 log.
And it becomes 20. So now we have minus 20 log omega over omega c, which looks like...
I got it. So I understand. So at high frequencies, it's going to have a slope. Firstly, there's a minus sign, so it's going to be a reducing function. And it's going to have a slope of minus 20 dB per decade at large frequencies because that square moved outside.
Exactly. So effectively, it looks, this expression is just minus. It looks exactly like this.
Okay, now let's do the sort of the intermediate case, because that was that was easy, but I'm sure you're hiding something by not talking about the intermediate case. All right,
I am hiding something.
All right, so let's try this. So at omega is equal to omega c or thereabouts, then that's going to become 1. And so it's going to be log of 2. So it's going to be close to 0, not exactly 0. Okay? And then you got the minus 10 log function. So I got it. So there it's going to be somewhere close to 0. Well, let me think about this.
Everyone at home sees what I'm doing.
Yes, you are. Okay, I'm being a little too difficult. I mean, this is the cutoff frequency, and we've just established that the half power point is 3 dB below, right? But that's what we did earlier. So it's easy enough. Really, the rules are pretty simple, okay? You know at the cutoff frequency, there's going to be a 3 dB point.
Yeah, so this is the minus 3 dB point. In other words, remember it was the half power point?
Yep.
Minus 3 dB. You would have expected that that's going to happen. That's your half power point.
Got it. Yeah, I was being a little too...
No, you're
cute.
Right. It was entertaining. But now let's point out two things. First one, only looking at the asymptotes told us almost everything there was to know, because as we knew, the center frequency here, or the cutoff frequency, was going to be minus 3 dB. So this curvature could have been inferred as long as I know this asymptote
Right.
and this asymptote.
But those asymptotes are fairly easy because I know at really low frequencies it's basically tending towards 0. So it'll be a straight line near the axis. And at high frequencies it's going at minus 20 dB per decade.
So the concept of just plotting the asymptotes we're going to come back to in a minute, because that's actually what a BodePlot is. A BodePlot is, look for an expression that looks like this, or rather these two components. We know that if I draw a straight horizontal line and this straight slope line, that'll tell me what I need to know, and then I can sort of mentally fill in the fact that there's a curve here. The other point is that we haven't really constructed the red line, which is actually the thing we were plotting. So for this transfer function, for this inductor, the result is this blue line going up to the right minus this one. So for very low frequencies...
Well, actually, to be clear, it's that blue line plus the dashed line,
plus.
right?
I keep forgetting that there's a minus there. You're absolutely right. It's this plus that.
Yeah, Michelle has trouble
there.
with negative signs.
I've trouble with negative signs today. But that's right. And so for very low frequencies, the red line just tracks the blue one because this is...
Because that's close to 0. Got it.
Exactly.
Yeah, so it's just going to be a negative number. Yeah.
And for very high frequencies, what's interesting is this slope is 20 dB, that slope is minus 20 dB. They just cancel out, you get a flat line.
Got it.
And in between, you just get this curvature that transitions from this phenomenon to the flat line. And so what you get is a high-pass filter.
Makes sense.
Now the high-pass filter has its half power point at the cutoff frequency, and it falls off at a rate of 20 dB per decade over here.
Okay, now I'm looking at some of the dashed lines you've got. Just to be clear, this is the minus 3 dB point, which falls at omega c. Over here, this is 20 dB, which would be the component coming from this first term. There's minus 20 dB here, and this comes from the same straight line. Got it.
Okay, now let's look at a couple things. So if this was a speaker and this was, say, 200 hertz, this would be 20 hertz, and you would be at minus 20 dB below whatever the cutoff frequency value is. And so, or rather, even if you want to look at it at the passband, so if the passband is here and we call that 0, you'd be 20 dB below, right?
Got it.
So just to kind of nail this home, I want to show you on the plot that the table we gave you. There we go. Minus 20 dB is 0.1 on a voltage decibel scale.
So it's basically
10th.
10%.
So we dropped to 10%, which might not be all that good, actually, right? I mean,
You might hear a 10% sound if it was delivered.
Right.
That's true.
You might want to be sharper. And so a lot of realistic filters have more than these two components to have what's called a higher order filter, and we'll talk about that.
But it
sharper
seems, let me
slopes.
guess as how that would work. That seems like, given that those squares and cubes help you to change the number, if I could get a square of a 20 dB term, it'll make it 40 dB.
Yeah.
So, okay.
And you'll see that's exactly what we do. That's how you get these, when you get these square terms, higher order, you'll get sharper slopes if you design it right.
All right.
Now let's do phase real quick, and we'll breeze through this a little quicker. But
Okay.
Just to remind ourselves, here's the RL circuit.
Yep.
There's the voltage out, and there's our transfer function. You want
Okay.
to take it from there?
Yeah, sounds good. So this is basically the same equation framework we'd set up earlier, but now from this transitioning to the polar coordinate system, we can calculate the phase. And in fact, it turns out this is the equation for the phase. Okay, so you should do this for yourselves to prove that that would be the phase. Now the phase is given as an arctan, and now here I've written it as it works out to be 90 degrees minus the arctan of omega c. That's what the phase is for this equation here. Okay? Now, let's think about what that means. Let's first recognize that we're starting at 90 degrees and we're subtracting something from it. Okay? So, Michelle, when we are looking at an omega of some very small value, okay? Let's say omega is a really small value. What does the arctan look like?
So for a very small value, what's going to happen for omega being very small, I'm going to get 0. It says we arctan of 0.
Yeah, and arctan of 0, because tan is a function that starts at 0 and goes upwards, is going to be 0. So in other words, we have 90 degrees minus 0, so we're going to start, for small omegas, we're going to be at 90 degrees. Okay? Now, let's consider really large omegas.
So very, 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 very large omegas, arctan ends up just going up to 90 degrees, right?
Right, and the reason is the tan function, when you get to 90 degrees, shoots up.
Oh, that's right.
Right?
That's right.
So the tan function shoots up. So when we have a very large input, what we're going to do is 90 degrees minus 90 degrees, which will tend towards 0. Okay? And you can do the same. You can do the calculation at 45 degrees at omega c, and you'll find that it's actually 45 degrees.
Oh, that makes sense. Sure.
So when you plot this all out, what you have is 90 degrees, okay, minus the arctan function. The arctan function looks like this, which means if you look at the red line, which is the combination of these two, we're going to start at 90 for small values of omega, end at 0 for large values of omega, and at omega c will be at 45 degrees. So that's it. That's how this works. It's not that difficult. Okay, now these are what we've looked at so far are sort of the accurate plots. The next step is going to be to look at BodePlots.
Yeah, and what I was about to say is, again, I would say make sure that you do all this on a piece of paper, these steps that we skip, because it's good practice.
Yep.
Okay, BodePlots. Dun dun. BodePlots are fairly straightforward. They're based on two observations. The first is that very often, let's take whatever the plot of this is. Don't worry about that it's up here. Just looking at it. The actual plot would look, the actual frequency response in decibels would look like this blue line. But very often, really the part that matters to us are the asymptotes, because from that we can reconstruct everything else that's going to go on. In other words, we know that it's going to tend towards this horizontal line for low omega, it's going to tend to this sloped line up here for high omega, and in between, it's going to transition between the two, and there's going to be a 3 dB or minus 3 dB point at the cutoff frequency. So just these two red lines allow me as an engineer to fill in the rest. Okay?
Yep.
That's the first observation. The second observation is that these plots can all be constructed as sums or subtractions of a number of different terms. In this case, there's two, just like we did in the last plot.
Right. So there's the straight line and the sloped line.
Exactly.
Fine.
So if we get good at tabulating them, right? So if we can good at making a table, a lookup table for most of the good ones, we can effectively break up a transfer function into its constituent parts and right away just know what to draw.
Got it.
Okay, so this case, and don't worry about the terminology simple zero, we're going to explain that in the next slide, but in this case we've got a transfer function that looks like 1 plus j omega over omega c to the nth power. I picked one arbitrarily. In the next slide we're going to give you a whole table of it.
Okay, let me guess. Because there's an nth power in there, I'm going to take the 20 dB term and multiply it by n, right?
Well, let's go through exactly what you did in the last slide. For large omega, this one doesn't matter.
Right.
Right? And you get this basically 20 log 10 of this term here, right?
Yep.
And so because there's an n here, you'll bring it down.
Yep.
And you'll get this 20 times n slope, just like you did before.
Yep.
If you don't remember, you just
got it.
go back and look. The only thing I didn't do here is I haven't written out this in decibel form. I just left it in its basic form to allow you to kind of think about it. But when I do 20 log 10 of this thing, you'll get for high frequencies, this will be a slope of 20n. And then for low frequencies, this goes to 1, this goes to 0.
Got it.
And so you get log of 20 log 10 of 1, so you just get the 0. Okay? The slope is the same thing. You guys can write at home, you can write out the arctan, write it out for yourselves, and you'll see that the phase will transition from 0 to 90 degrees times n. So this will, if n is 1, this will be 90 degrees. If n is 2, this will be 180 degrees. And it'll just straight line transition between the two. It's an asymptote. It's not actually what the real response is. The real response is curved, goes through this 45 degree point exactly at the cutoff frequency, right, 45 times n, and then slopes up a bit as it slopes to horizontal, essentially.
I get it. So, and the way we've done the asymptote is basically 1 decade below the cutoff frequency, we go 45 degrees down. 1 decade above the cutoff frequency, we go 45 degrees up.
Right.
Easy.
Now, this is very easy to explain. It's a very good job for us. BodePlots are really easy as an instructor to explain. And in the next slide, we're going to give you a table. But they're really hard to do efficiently, because you're watching us now and it all makes sense. You're really going to need to practice this. It's not difficult. You're going to do a few of them. But if you don't, it's going to make a real difference. So here's a table of a bunch of these, and we're just going to walk you through so you can think of them, and we're going to introduce some terminology.
Right. So let's start with the easy one, okay? And the easy one I'm going to start with, and this time I'm not going to do the work. I'm going to do the easy one and then hand the harder ones off to Michelle, is I'll do the constant. Ha-ha!
Aha!
So the constant... Well, what do you think? The constant is just going to be a flat line, right? Because it's something that has no frequency dependence.
It's frequency independent, that's
It's
right.
frequency
So it's-
independent, which means whatever the magnitude is going to be fixed with frequency, and whatever the phase is going to be fixed with frequency.
Exactly. 20
Okay.
log of a number.
All right, Michelle, you get to do the next one.
Okay, so to do that, let's introduce two terms, zero and pole. Zero is when you write out your transfer function and you clean it up into the standard form, which is these j omega over omega c's, okay? You're going to find things in your numerator and you're going to find things in your denominator, okay? Now, and then there'll be a constant. I mean, it could be 1, but generally speaking, there'll be some constant that you can factor out and just call k times everything else. Anything in the numerator we call a 0, okay?
Right. Why?
Well, why do you think what happens? Why do you at what point does the numerator go to 0 in the log scale?
In the log scale, the numerator will go to 0.
Or when does the transfer function? Sorry, when does the
Yeah,
transfer function go to 0? When it's called a 0. When this expression is at the corner frequency, right? Because then I get log of 1.
Oh, okay, I
So
get it.
these points, the transfer function has, if it was just that, the transfer function would go to 0, because I have 20 log
Yep.
omega over omega c, at omega c it would go to 0. It's called 0.
Oh,
And
got
the
it.
poles are the things in the denominators. Now, you're going to run into this in control theory in a lot more detail, and it's actually very rich. This is a really rich area of applied mathematics, a lot of fun if you get into it. And it has a lot of bearing on analog circuit design. You know, how to design circuits so that they have poles and zeros in specific places becomes a very, very, very important thing. But for the moment, all you need to know is that the expressions in the numerator that come out this way are called zeros, and if they're in the denominator, that's why there's we have this little minus sign here. They're called poles, and there's different types. So there's a simple zero here. A zero at the origin here. I'll explain why it's called that in a minute. There's a simple zero, and then there's quadratic and higher order ones, but this is a quadratic one. So here's what it looks like. This is going to be alien to you when you start, but it's really pattern recognition when you're first learning it.
So let me see if I understand this. So we're doing various things. First, we're taking advantage of the fact that we can construct BodePlots by adding together the individual factors. Since we're going to log scale, instead of having to multiply the individual factors, it becomes adding together. So the idea is I can take some complex transfer function, plot up the individual things like the constants, the zeros, the poles, etc., and then just figure out the net effect of all of those put together.
Yeah, and we're going to do a lot of examples to really get this clean. But when you're looking at the actual transfer function, before you do the decimal conversion, whatever's in the numerator is the zero or zeros, and whatever is in the denominator are poles.
So that's a definition. Things in the numerator like that are zeros. Things in the denominator like that are poles.
Right.
If you don't understand why we call them zeros and poles, just consider how a numerator affects a function and a denominator affects a function.
Right.
When a numerator goes to a term in the numerator goes to 0, the function goes to 0. When a term in the denominator goes to 0, the function explodes to a high value.
Yeah.
Hence the term zero and pole.
So let's look at some examples, and all of you can do this now. What does this expression look like when we do our standard decimal plot form?
Well, this is fairly straightforward, and we're going to plot it with all of these plots are done with respect to some sort of reference frequency. Now, in this particular case, in the j omega term, I'm going to see when does it go to 0 dB. Well, it goes to 0 dB when omega is equal to, well, I want that function to equal to 1. So it's going to happen at 1, right?
So, right. So what you're saying is that this thing becomes 0 at the origin, so that on the omega scale, at 1, you have a 0 crossing on the dB
Yep.
scale. And you're going to have a...
And the reason for that 1 to 0 thing is because it's a log, and log of 1 is 0.
Mm-hmm.
Got it.
Those of you at home, this is the part where we're doing our best to slow it down and break it up and unpack it for you, but it does require a little bit of work. So you're going to have to do some. Never fear, the next module is just examples of this. So you're going to walk through and just do all of it for you very slowly.
But let's do it again one more time to be sure. Okay, let's take the 0 again, the 0 at the origin.
You want to do this one? Okay.
Yeah, let's stick with that one more time.
So do 20 log of this.
Yeah, let's do 20 log of that. And forget the n for now.
Let's pretend it's 1.
Yeah, let's pretend it's j omega. 20 log of j omega. So first question is, at what value does 20 log go to 0? Well, it'll go to 0 when the term inside the log is 1. Mm-hmm. Okay, and the term inside the log is 1 because we're going to be taking the the magnitude. So the j's disappear, right?
That's
So
right.
that's going to be 1 when omega is 1. So for this particular form, we know that the magnitude is 0 dB when omega is equal to 1. Further, because we're doing 20 log of that, we know that the slope is going to be 20 dB per decade.
For n equals 1, yeah.
For n equals 1. Now let's take that next step. If n were not equal to 1, it would still go to 0 at 1, but the slope will be 20 times n because the n in the power will move out of the log to be a multiple.
Exactly.
Okay. Now, for poles, it's going to be exactly the same framework, except because it's minus n, it's going to slope downwards.
Perfect.
Okay.
Now the simple zero,
We've done that already, right?
Yeah, we've done an example that's very similar to that. And so here, if this expression is in the numerator, it's a 0. If the expression is in the denominator, notice we've cast in that form where it's 1 over something. It's already in the denominator. If you see this, that's a simple pole. Remember why we're doing this. When you convert it to log, if I have an expression that has this in the numerator, j omega raised to the n power, and multiplied by this, in other words, you'd get this 1 plus j omega over omega c to the n in the denominator, when I do the log, I'm going to break those two apart. So I'm going to figure this one out first, we just did. And here's an example of a simple pole. And what you should do is convince yourself, just as we did in the last example, that for low omega, this is going to be 0 for this expression. And for high omega, it's going to basically asymptote to a minus 20 dB decade.
Again, let's do this one again carefully just to make sure you do it. And let's do the simple pole just because that's what Michelle's talking about, all right? So for the simple pole, remember that this is the function that has two different asymptotic regions. For really low omega, okay? For really low omega, that is going to asymptote towards 0 dB because the omega over omega c will disappear and we'll be left with 1, which at log function is 0, so 20 log of that is going to be at 0 dB. So for low omega, it's a flat line at 0. For high omega, the 1 disappears, and so it just becomes j omega over omega c, which in the magnitude form is just going to be omega over omega c, which means that is going to go, given that there's a 20 log, it's going to go as 20 dB per decade. If we raise it to a power n, it's going to be 20 n dB per decade.
Well,
now, there's a minus sign there
Right.
because it's in the denominator.
That's right. It's a pole, so it's minus n. So as you bring it down, it's minus 20 n dB per decade, so it slopes down. Perfect. This holds for all of these. You can explore this to your heart's content. We'll do examples with quadratics for sure, but we just want you to get used to looking at this. We haven't talked about the phases, but the phases really follow the rules as we've seen in the one or two examples we did. So, for example, just to state it out loud, a 0 at the origin has just a constant 90 times n. These that have corner frequencies will then have these 90 n degree phase shifts either up or down.
So what we do recommend is before you quit this module, before you move on to the next module anyway, take each of these terms that you see plotted over here and convince yourselves that what we have plotted is correct. And the way to convince yourself is actually figure out the asymptotic shapes of each part of those curves and make sure that they match as far as you're concerned.
That's exactly right. So here's what we're going to do. We're going to give you all a break, and then we're going to come back in the next module, and we're just going to do examples of BodePlots and show you how to put this to work, because that's really what's required, is a little bit of exercise. So thanks for sticking with us.